Welcome to this session. Today, we are tackling a fascinating problem titled minimum cost to repair edges. In this problem, we will explore how to determine the minimum cost needed to repair broken edges in a graph, ensuring it remains fully connected. Let's dive into the details and approaches to solve this problem step by step. In this problem, we are working with an undirected graph that consists of n nodes labeled from 1 to n. Within this graph, some edges are functional, while others are broken. You are provided with two lists to represent the graph's current state. The first list, edges, contains the functional edges, where each edge is denoted as U, V, meaning there is a working connection between nodes U and V. The second list, edges to repair, contains the broken edges. Each broken edge is represented as U, the cost, where U and V are the endpoints of the edge, and cost is the price required to repair it. Our task is to repair some of the broken edges so that all nodes in the graph are connected. In graph terms, we want to create a single connected component, also known as a spanning tree. The objective is to achieve this while minimizing the total repair cost. If it's impossible to connect all nodes, we return -1. To summarize, the input to the problem includes the number of nodes, n, the list of functional edges, and the list of broken edges with their repair costs, edges to repair. The output is a single integer that represents the minimum cost to connect all nodes in the graph. If it's not possible to connect all nodes, the output should be -1. Let's explore some examples to clarify how the solution works. In the first example, we are given n equals 5, with 3 functional edges, 1, 2, 2, 3, 4, 5, and 3 broken edges, 1, 3, 5, 1, 4, 10, 3, 5, 7. The output for this example is 17. Here's an explanation of the first example. The graph initially has 3 working edges, 1, 2, 2, 3, and 4, 5. However, the graph is disconnected, as there are 2 separate components. To connect all nodes into a single component, we need to repair some of the broken edges. The optimal choice is to repair the edges 1, 3, with a cost of 5, 3, 5, with a cost of 7, and 1, 4, with a cost of 10. Adding these repair costs together gives us a total of 5 plus 7 plus 5 equals 17, which is the minimum cost required to connect all nodes. In the second example, we are given n equals 6. The functional edges are 1, 2, 2, 3, 4, 5, and the broken edges are 1, 4, 8, 3, 6, 2, 5, 6, 10. The output is 20. To understand this result, let's analyze the graph. Initially, the graph has 3 working edges, 1, 2, 2, 3, and 4, 5. Similar to the first example, the graph is disconnected, and we need to repair edges to form a single connected component. The best edges to repair are 1, 4, with a cost of 8 and 3, 6, with a cost of 2. These repairs connect the components, and finally, we must also repair 5, 6, with a cost of 10. The total cost is 8 plus 2 plus 10 equals 20. Now, consider the third example where n equals 3, and there are no functional edges. The graph is completely disconnected, so we must rely entirely on repairing edges to connect all nodes. The broken edges provided are 1, 2, 15, 2, 3, 20, 1, 3, 30. The output here is 35. To achieve this, we repair the edges 1, 2, with a cost of 15 and 2, 3, with a cost of 20. These 2 repairs are sufficient to connect all nodes, resulting in a total cost of 15 plus 20 equals 35. This is the minimum cost required in this case. Finally, let's discuss the problem's constraints and edge cases. The number of nodes, n, can go up to 10⁻⁴, and the number of edges, both functional and broken, can reach up to 10⁻⁵. Each repair cost is bounded between 1 and 10⁻⁶. Edge cases to consider include scenarios where no repair is needed because the graph is already connected, or where it is impossible to connect all nodes even after repairing all available edges. Additionally, for a single node graph, the cost is always 0, as it is trivially connected. Efficiently solving this problem requires an algorithm with a time complexity of approximately n plus edges to repair, *log edges to repair, to handle the upper limits of these constraints. To solve this problem, we considered multiple approaches, starting with the brute force method. The intuition here is simple. We generate all possible subsets of broken edges, calculate the cost of repairing each subset, and check if the repaired graph forms a fully connected structure. Essentially, we look for the subset with the minimum repair cost that ensures connectivity. While this approach is straightforward in concept, it's computationally infeasible for large inputs because the number of subsets grows exponentially, at a rate of 2 to the power of the number of broken edges. On top of that, checking connectivity for each subset adds additional complexity, making this approach impractical for real-world applications. Shifting gears, a more efficient strategy involves using a greedy algorithm combined with disjoint set union, or DSU. The key idea here is to treat the problem as a variation of the minimum spanning tree problem. By leveraging the properties of DSU, we can minimize the cost of repairs while keeping all nodes connected in a much more computationally efficient way. Now, let's break down how the greedy plus DSU approach works. First, we treat the graph as a mix of intact edges and reparable edges. Intact edges are edges that already exist and don't require any repair, so we can think of their cost as zero. Next, we sort all edges, both intact and reparable, by their cost in ascending order. Once the edges are sorted, we use DSU to process them one by one. For each edge, we check if it connects two previously unconnected components. If it does, we add the edge to our solution. As we process, we keep track of the total repair cost and ensure that all nodes in the graph are eventually connected. This way, we build the minimum spanning tree while minimizing repair costs. The computational efficiency of this approach comes from the fact that sorting the edges takes E log E time, and DSU operations like union and find are nearly constant time due to path compression. An alternative strategy could involve using Prim's algorithm with a priority queue, which is another MST-based method. Here, we iteratively expand the tree by adding the cheapest edge connected to it. However, handling intact and reparable edges in Prim's algorithm requires some additional pre-processing, which can make the implementation slightly more complex. Given these options, we chose the greedy plus DSU approach as our solution strategy because it strikes the right balance between efficiency and simplicity. Sorting edges and performing DSU operations are computationally feasible even for large inputs, which makes this approach scalable to graphs with thousands of nodes and edges. The simplicity of implementation is also a significant advantage, as treating intact edges as zero-cost edges integrates seamlessly into the DSU-based MST algorithm. Additionally, this method aligns perfectly with the goal of minimizing repair costs while ensuring connectivity. One of the key insights here is that the problem essentially revolves around constructing a minimum spanning tree, with the added complexity of distinguishing between intact and reparable edges. By sorting edges by cost, we ensure that the cheapest repair options are always considered first, which is the core principle of a greedy algorithm. This insight was a pivotal moment in simplifying the problem and arriving at an efficient solution. Finally, let's compare the trade-offs of the different approaches. The brute force method, while conceptually simple, is computationally infeasible for large graphs due to the exponential growth in subsets and the overhead of checking connectivity. Prim's algorithm is an effective alternative, but it introduces additional complexity when handling zero-cost edges, making it less intuitive to implement in this context. On the other hand, the greedy plus DSU approach offers the best of both worlds. It's efficient, scalable, and relatively easy to implement. By focusing on the key principles of minimum spanning tree construction and leveraging the DSU data structure, this approach emerges as the ideal choice for solving this problem. It balances computational efficiency with practical simplicity, making it highly suitable for competitive programming scenarios and real-world applications alike. To tackle the problem of minimizing the cost to repair edges and fully connect the graph, we start by representing the graph in a way that incorporates both intact and broken edges. An adjacency list or adjacency matrix is a great choice for this purpose. For intact edges, which require no repair, we assign a cost of 0. For broken edges, we store their respective repair costs. Once the graph representation is complete, we compile a list of all edges, where each edge is represented by its two connected nodes and the associated cost. The next step is to sort this edge list in ascending order based on the cost. This prioritization ensures that we always consider the least expensive repairs first, which is a key principle of constructing a minimum spanning tree. To manage connectivity during the process, we initialize a union-find data structure, where each node starts as its own parent. This will help us efficiently determine which nodes belong to the same connected component as we proceed through the algorithm. The union-find data structure is optimized using two techniques, path compression and union by rank. Path compression ensures that the find operation, which determines the root of a node, is extremely fast by flattening the structure of the tree over time. Union by rank, on the other hand, ensures that when two components are merged, the smaller tree is always attached under the root of the larger tree. This keeps the structure balanced and efficient. With the data structure in place, we can now implement Kruskal's algorithm to construct the minimum spanning tree. We start by initializing two variables, total_cost to track the cumulative cost of the edges added to the spanning tree and edges_use to count the number of edges in the tree. Iterating through the sorted edge list, we consider each edge one by one. For an edge connecting nodes U and V, we use the find operation to check if the nodes already belong to the same connected component. If they are not connected, we add the edge to the spanning tree, update the total cost, and perform a union operation to merge the components. We also increment the count of edges used. If the number of edges used reaches n1, where n is the total number of nodes, the graph becomes fully connected, and we can terminate early. Kruskal's algorithm is particularly suitable for this problem because it directly addresses edge costs and connectivity. Its greedy nature ensures that we minimize the repair costs while building the spanning tree. The efficiency of the union-find data structure, with its nearly constant time operations, contributes to the algorithm's overall performance. Additionally, the algorithm allows for early stopping as soon as the graph is fully connected, saving unnecessary computations. It's also robust in handling cases where the graph cannot be connected. By checking the total number of edges added at the end, we can determine whether all nodes are part of a single connected component. For storing the graph, an adjacency list is an efficient choice, while the edge list simplifies sorting and processing by cost. The time complexity is dominated by the sorting step, which is O, m log m, for m edges, and union find operations add a negligible overhead of O, m asterisk alpha, n, where alpha, n, is the inverse Ackermann function. This makes the overall complexity O, m log m. Space complexity is linear, requiring storage for the union find data structure and the edge list, resulting in O, n plus m, space usage. When considering edge cases, the algorithm handles various scenarios effectively. For disconnected graphs where no combination of edges can connect all nodes, it returns -1. If the graph is already connected initially, the cost is 0, as no repairs are needed. For a single node graph, it is trivially connected by definition. In cases where no reparable edges exist, the algorithm identifies that all edges are intact and skips repairs, again returning 0. To implement this, we start by combining the intact edges and the edges requiring repair into a single list. Intact edges are recorded with a repair cost of 0, while the broken edges retain their specified costs. After compiling this list, we sort it in ascending order of cost. Following this, we initialize the union find data structure with a parent array, where each node is its own parent, and a rank array initialized to 0. This setup ensures that the data structure is ready to efficiently manage connected components as we begin processing the edges. After initializing the union find data structure, we define the find function to locate the root of a given node. Path compression is applied during this process to flatten the structure of the tree, which accelerates future operations. The union function merges two components by connecting their roots, using the rank to decide which root becomes the parent. If the ranks are equal, one root is arbitrarily chosen as the parent, and its rank is increment. With these functions in place, we proceed to construct the minimum spanning tree. Starting with total_cost set to 0 and edges_use set to 0, we iterate through the sorted list of edges. For each edge, we check if the nodes it connects belong to the same component using the find operation. If they are not connected, we add the edge to the spanning tree by performing a union operation, update the total cost by adding the edge's cost, and increment the edge count. This process ensures that we only add edges that contribute to connecting previously disconnected components. As we add edges to the spanning tree, we monitor the count of edges used. If this count reaches n1, where n is the number of nodes in the graph, the entire graph becomes fully connected. At this point, we can return the total cost, as the minimum spanning tree is complete. If we exhaust the edge list without reaching N1 edges, it means that the graph cannot be fully connected with the given edges, and we return -1. This final check ensures that the algorithm handles disconnected graphs gracefully. By following this approach, we efficiently compute the minimum cost to repair the edges while guaranteeing that all nodes are part of a single connected component, provided it is possible to do so. To solve the problem of finding the minimum cost to repair edges, we start by preparing the graph and organizing the repair costs. First, we identify the edges that need repair using a set to store these edges in a normalized format, ensuring the smaller node always comes first. Then, we create a dictionary mapping each broken edge to its repair cost. After that, we construct the graph by including only the intact edges initially, assigning them a cost of 0 since they don't require repair. We then add the broken edges along with their respective repair costs. Next, we move to implementing Kruskal's algorithm to find the minimum spanning tree, or MST. We begin by sorting all edges based on their costs. Additionally, we initialize the union find structure to manage connected components, where each node is initially its own parent, and we set the rank of all nodes to 0. The find function is implemented to locate the root of a node, applying path compression to optimize the structure over time. The union function is then defined to merge two disjoint sets, ensuring that the smaller tree is attached under the root of the larger tree to maintain efficiency. If the ranks are equal, we arbitrarily choose one root and increment its rank. With these foundational operations in place, we initialize the total cost of the MST to 0 and a counter to track the number of edges used. We then iterate over the sorted edges, and for each edge, we check if the nodes it connects are already part of the same connected component. If not, we use the union operation to merge their components, add the edges cost to the total, and increment the edge counter. Once we have used N1 edges, meaning all nodes are connected in the MST, we return the total cost. If it's not possible to connect all nodes, we return -1 as the result. This ensures that we either find the minimum repair cost to connect the graph or determine that it's impossible to do so. Here, we begin by defining our solution class in the main method, which calculates the minimum cost to repair edges in a graph. The first step is to prepare the graph and repair costs. We use a hash set to track the edges that need repair and a hash map to store the repair costs for these edges. For every edge in the edges to repair array, we extract the source node, destination node, and repair cost. We then create a unique key for each edge using the createEdgeKey helper method, which ensures consistent formatting regardless of the order of nodes. These keys are added to the edge set, and their costs are stored in the repair costs map. Next, we initialize a list called graph to hold all the edges. We start by adding intact edges, which do not require repair, with a cost of 0. For each edge in the original edges array, we check if it exists in the edge set. If it doesn't, we add it to the graph as a cost-free edge. After adding the intact edges, we proceed to incorporate the broken edges. Using the entries in the repair costs map, we split each edge key to retrieve its nodes, then convert these string values into integers. These edges, along with their associated repair costs, are appended to the graph list. With the graph prepared, we move on to applying Kruskal's algorithm to find the minimum spanning tree, or MST. The graph is sorted by the cost of the edges to ensure we process the least expensive edges first. We also initialize two arrays, parent and rank, which help track the connected components in the graph. The parent array begins with each node being its own parent. We then declare variables for the total repair cost and the number of edges used in the MST. As we iterate over the sorted graph, we check whether the nodes connected by the edge belong to different components by using the find method. If they do, we connect these components using the union method and add the edges cost to the total cost variable. When an edge is added to the MST, we increment the edges used counter. Once this counter matches N1, where N is the total number of nodes, it means all nodes are connected. At this point, we return the total cost as the result. If the loop finishes without connecting all nodes, which would indicate that the graph is disjoint, we return -1 to signal that it's impossible to connect all nodes. Moving on to the helper methods, createEdgeKey is responsible for generating a consistent key for each edge. By ensuring that the smaller of the two nodes always comes first, this method avoids duplicate keys for bidirectional edges. The find method performs path compression to efficiently locate the representative parent of a node, helping to speed up union find operations. Finally, the union method merges two components by attaching the smaller tree to the larger tree based on their ranks. If the ranks of both components are equal, we arbitrarily choose one as the new root and increment its rank. This rank-based union ensures that the tree remains balanced, which optimizes the performance of the union find operations. With these helper methods in place, Kruskal's algorithm can efficiently construct the minimum spanning tree, ensuring that the graph is fully connected at the minimum possible repair cost. To solve this problem, we start by preparing the graph and determining the repair costs. The input specifies n equals 5 nodes and 2 sets of edges, intact edges and edges that need to be repaired. First, we identify the broken edges from edges to repair and store them in a set called edge_set, which contains 1, 2, and 4, 5. We also create a dictionary repaired_cost that maps these broken edges to their repair costs. 1, 2 costs 12, and 4, 5 costs 20. Next, we construct the initial graph. Intact edges are added with a cost of 0, so edges like 1, 3, and 2, 4 are represented as 0, 1, 3, and 0, 2, 4. Then, we include the broken edges with their respective repair costs, resulting in a graph representation of 0, 1, 3, 0, 2, 4, 12, 1, 2, 20, 4, 5. To ensure we process the edges efficiently, the graph is sorted based on the costs, resulting in the sorted graph 0, 1, 3, 0, 2, 4, 12, 1, 2, 20, 4, 5. With the graph prepared and sorted, we proceed to find the minimum cost to connect all nodes using Kruskal's algorithm. First, we initialize the union find structure. The parent array is 0, 1, 2, 3, 4, 5, where each node is its own parent initially, and the rank array is 0, 0, 0, 0, 0, 0, which tracks the depth of the trees. Now, we process the edges in the sorted order. Starting with the edge 0, 1, 3, we connect nodes 1 and 3 since they belong to different components. This operation incurs no cost, keeping the total cost at 0. Next, we process 0, 2, 4, and connect nodes 2 and 4, again at no cost. Moving to the edge 12, 1, 2, we connect nodes 1 and 2, which adds a cost of 12 to the total. Finally, the edge 24, 5 connects nodes 4 and 5, adding 20 to the total cost. At this point, all nodes are connected, and the total repair cost is 32, which is returned as the final output. In this example, the input specifies n equals 4 nodes and 2 disconnected components, one with edge 1, 2, and another with edge 3, 4. Both edges are broken and need repair, which is specified in edges to repair with costs of 5 and 10, respectively. We start by preparing the graph. The broken edges are stored in edge_set, and their respective repair costs are mapped in repaired_cost. Since there are no intact edges, the graph initially contains only the broken edges with their repair costs 5, 1, 2, 10, 3, 4. Next, we sort the graph by cost, resulting in the same order 5, 1, 2, 10, 3, 4. Using Kruskal's algorithm, we initialize the union find structure with parent equals 0, 1, 2, 3, 4, and rank equals 0, 0, 0, 0, 0. The edge 5, 1, 2 is processed first, connecting nodes 1 and 2 at a cost of 5. Then, the edge 10, 3, 4 connects nodes 3 and 4, adding 10 to the total cost, which becomes 15. However, not all nodes are connected, so it is impossible to form a single connected graph. The output is therefore -1. Now, consider a simpler scenario where all edges are intact. Here, the input specifies n equals 3 nodes and edges 1, 2, and 2, 3. Since there are no edges to repair, we only need to process the intact edges. First, we prepare the graph by assigning a cost of 0 to all intact edges. This results in a graph representation of 0, 1, 2, 0, 2, 3. Sorting the graph by cost does not change the order, as all edges already have the same cost of 0. With the graph ready, we can proceed to the next steps. Using Kruskal's algorithm, we initialize the union find structure with parent equals 0, 1, 2, 3, and rank equals 0, 0, 0, 0. We process the edges in the sorted order. The first edge, 0, 1, 2, connects nodes 1 and 2 at no cost, keeping the total cost at 0. The second edge, 0, 2, 3, connects nodes 2 and 3, again at no cost. At this point, all nodes are connected, and the total repair cost remains 0. This is returned as the final output of the algorithm for this example. In analyzing the time complexity of our solution, we can break it down into several key steps. First, we process the edges to repair array to build two structures, edge_set and repaired_cost. Since this involves iterating through our edges and edges to repair, both operations require O(R) time, resulting in a combined cost of O(R) for this step. Next, we process the edges array, which contains m edges. For each edge, we check whether it belongs to the edge_set, which is done in constant time due to the hash-based implementation. Iterating through all m edges therefore requires O(M) time. After that, we add the edges from repaired_cost to the graph, which involves at most r entries, taking O(R) time. Finally, we sort the graph, which now contains up to m plus r edges. Sorting these edges based on their weights has a time complexity of O(M plus r) log m plus r. These steps give us a clear breakdown of the time complexity for the initial processing stages of the algorithm. Now let's examine the time complexity of using Kruskal's algorithm to construct the minimum spanning tree, MSA. Kruskal's algorithm processes all the edges in the sorted graph, which contains at most m plus r edges. The algorithm relies on the union-find data structure for two primary operations, find and union. Each find operation has an amortized time complexity of O alpha n, where alpha n is the inverse Ackermann function that grows extremely slowly, effectively making it almost constant in practical scenarios. Similarly, each union operation also has an amortized complexity of O alpha n. For each edge in the graph, we perform at most one find operation for each of its two nodes, and possibly one union operation. This results in a total complexity of O(M plus r) alpha n for Kruskal's algorithm. When we sum up the time complexities of all the steps, we get O(M plus r) for processing edges, O(M plus r) log m plus r for sorting, and O(M plus r) alpha n for Kruskal's MSA construction. Since sorting dominates, the overall time complexity of the solution is O(M plus r) log m plus r. Let's now consider the space complexity of the solution. First, we account for the data structures used to process the edges. The edge_set stores up to r edges, requiring O(R) space. Similarly, the repaired_cost dictionary, which holds repair costs for up to r edges, also requires O(R) space. The graph structure, which contains up to m plus r edges, takes O(M plus r) space. Next, we look at the union-find data structure. The parent array, which is used to keep track of connected components, requires one entry per node, resulting in O(N) space. Similarly, the rank array, which helps optimize the union operation, also requires O(N) space. Additionally, the sorting operation for the graph requires auxiliary space of O(M plus r). When we combine all these components, the overall space complexity of the solution is O(N plus M plus r). Finally, let's compare our optimized approach to a brute force method. A naive approach would involve generating all possible subsets of edges, calculating their costs, and checking if they form a connected graph. This would result in an exponential time complexity of O(2)M plus r, which is clearly infeasible for larger inputs. In contrast, our optimized solution leverages Kruskal's MSA algorithm and the union-find data structure to reduce the time complexity to O(M plus r) log m plus r, and the space complexity to O(N plus M plus r). When we analyze the best, average, and worst cases for this algorithm, we find that all of them exhibit the same asymptotic bounds. This is because the algorithm always processes all edges and sorts them, regardless of their weights or distribution. From a mathematical perspective, the dominant term for time complexity is sorting the graph, which takes O(M plus r) log m plus r. The union-find operations have a negligible impact due to the extremely slow growth of alpha n. Similarly, the space complexity is driven by storing edges and the union-find structures, giving us O(N plus M plus r). When tackling this problem, there are a few common mistakes to avoid. One of the most frequent is overlooking edge cases. Scenarios like disconnected graphs, single-node graphs, or graphs with no edges are easy to miss but can lead to incorrect solutions if not explicitly tested. Additionally, it's important to distinguish between fully connected and partially connected graphs. A fully connected graph ensures that all nodes can be reached from any other node, so you need to verify connectivity carefully in your solution. Another pitfall is inefficiency in brute force approaches. Generating all subsets of edges without excluding irrelevant ones can waste significant computation time, especially if some subsets are guaranteed to exceed the optimal cost. Mistakes in union-find implementation, such as failing to apply path compression or union by rank correctly, can also lead to incorrect results, so always validate your logic with small test cases. Finally, in greedy algorithms like Kruskal's or Prim's, forgetting to prioritize edges with lower weights can result in suboptimal solutions. Always ensure you're accounting for edge weights while maintaining graph connectivity. Now, in terms of interview insights, understanding foundational graph algorithms like depth-first search, breadth-first search, and union find is crucial. These form the backbone of most graph-related problems, so a solid grasp of them is essential. It's also important to highlight the trade-offs between brute force and greedy approaches. While brute force guarantees correctness, it's often computationally expensive, whereas greedy algorithms like Kruskal's or Prim's are much more efficient for weighted graphs. During an interview, it's a good idea to communicate your thought process clearly. Start with a brute force approach if necessary, explain its limitations, and then transition to a more optimized solution to showcase your problem-solving adaptability. Testing early and often is another key strategy. Small test cases with just a few nodes can help you quickly identify and fix implementation bugs. For further practice, related problems like LeetCode 1584, 323, 684, and 1135 provide excellent opportunities to refine your understanding of graph connectivity, cycle detection, and minimum spanning trees. For alternative approaches, greedy algorithms like Kruskal's are often the go-to solution for finding minimum spanning trees. This method sorts edges by weight and uses union find to check connectivity. With a time complexity of O(E*log E, where E is the number of edges, it's highly efficient, though the union find implementation requires careful attention to avoid errors. Prim's algorithm is another greedy option, which uses a priority queue to add edges one at a time. Its time complexity, O(E plus V*log V), makes it well suited for dense graphs, though it can be slightly more complex to implement compared to Kruskal's. Dynamic programming offers another alternative, especially in cases where subsets of edges or nodes need to be optimized. While this approach can be useful for specific variations, it tends to be computationally expensive and less scalable for larger graphs. Each approach has its trade-offs, so understanding when to apply each is crucial for solving graph problems effectively. In conclusion, this problem is a fantastic exercise in graph theory and optimization. We covered the key concepts, summarized the important takeaways, and highlighted the relevance of these techniques in coding interviews. Thank you for joining today's session. Don't forget to like and subscribe for more problem-solving videos. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!